Here's the game of life spinner. So if we start this wheel spinning with a certain velocity and it slows down, then we need to see where does the wheel stop. And so in this picture, it starts on the 7. So we'll give the wheel some initial velocity and it'll decelerate. And then once velocity equals 0, we check where the wheel landed. So first, let's write down our problems or our formulas for what we have done before. First set of formulas we have had if acceleration is constant. Then we have alpha equals d omega dt. Let's see, equals d squared theta dt squared equals omega d omega d theta. And actually this doesn't matter if acceleration is constant or not, so I'm going to erase that. And then we have the other one for omega equals d theta dt. Now, if acceleration equals constant, so this will be constant alpha, then we'll have omega equals omega initial plus alpha t, and theta equals theta initial plus omega initial t plus 1/2 alpha t squared. So these look real similar to the projectile motion problems. So we'll start out now with this game of life spinner and say if we're given the initial velocity that we start the wheel spinning with, and that it starts in this position shown, and then a deceleration, then we need to find time to stop wheel. So we'll call that TS for T stop. Or actually I'll call it TF for T final. So T final and theta final. And basically we want to know like what number does the wheel stop on. Okay, so a couple values we need to have here. Let's say omega initial starts with 10 radians per second. And then alpha is -3. Or no, let's say -2. -2 radians per second squared. Okay, so steps to solve this problem. It asks us to find the stopping time and the stopping angle, and basically stopping position. Now we know here that we were given alpha is -2 radians per second. Let's say that's a constant. So we can use the constant acceleration equations. So we'll use this first equation to find the stopping time. We know that stopping time is when omega equals 0. So we'll use the omega equation, set it equal to 0, solve for time. And then we can plug that into the theta equation, find theta. And then once we found theta, we'll know how much the wheel has rotated. And then we'll be able to tell based on the rotation of, say, where the 7 is, then we can count back or forwards and find which one is on the spinner. So let's say step 1, use omega, solve for t. So we'll have omega equals omega initial plus alpha t. And this is going to equal omega initial, so we put in the 10 radians per second, and then alpha decelerating at 2 times t, and we know that the wheel stops when angular acceleration equals 0. So 0 equals 10 minus 2t. And so we can rearrange and say that 10 equals 2t. So t final equals 5 seconds. So t final is 5 seconds. So now we can take this 5 seconds and plug into the theta equation and find the angle. So step 2 is use the t, plug in, get theta. So we have theta equals theta initial plus omega initial t plus 1/2 alpha t squared. So figuring out theta initial, we weren't given it in the problem, but we were given basically that the wheel starts in this position. So what we'll say is that we'll track the position of the 7, and we'll just say that right here is 0, and then how far has the 7 gone? We'll say that the wheel starts at 0 degrees. So if we're tracking from the initial position, this theta is basically change in angle. So we can just rewrite this and say change in angle equals omega initial t plus 1/2 alpha t squared. So omega initial is 10, and now we have the t, which is 5 seconds. And then we'll have negative 1/2 times 2 times 5 squared. So that cancels. So we have 50 minus 5 squared, which is 25, equals 25 delta theta. So this 25 has units of radians. So we know that the wheel has spun 25 radians, but like, what does that actually mean? What position has it stopped at? So in order really to find that, we have to figure out the number of revolutions, and then we can see here that there are 10 numbers on the wheel. And so each number takes up approximately 1/10 of a revolution. So if it is 360 degrees in the whole circle, then divide that by 10, each section is 36 degrees. Or each section is 1/10 of a revolution. So now we need to actually convert, we'll say step 3, convert to revolutions and count slots, which basically the slot is each number. So to convert to revolutions, we know there are 2 pi radians in 1 revolution. So we'll say that 25 radians times 1 revolution over 2 pi radians. So put that into a calculator. How many revolutions do you get? So this is 3.97 revolutions. So basically it's spun around almost 4 times. This is so close to 4 that we're going to say like it's still within the range of one single number. So 3.97 revolutions. So then that means that the wheel has gone around 4 times, and so it's stopped again on 7. So because it was so close to 4, then the wheel is still in that range for the 7. So we'll say stop. All right, so if it started on the 7, you spun it that far, it stopped on 7. So any questions on this problem using the constant acceleration equations for fixed axis rotation? All right, so if this had been something different, like say 3.9, then that would be different because we know that the wheel, every 10th of a revolution, the wheel's on a different number. So if it had spun around so that it was only 3.9, then the 7 wouldn't have gotten all the way there. We would still be on 6. So like minus 0.1 for every number. So then if it was 3.8, it would have been on 5. 3.7 would have been on 4, and so on and on and on until like 3.1 would have been on 8, and 3.0 would have been on 7. So each 10th of a revolution, it's going to be on a different number. Susan has a question. We assume no friction. Yes, there is friction. The friction is what's causing the deceleration. So we weren't given a value for friction coefficient. We also weren't given a mass or a force because right now we're still in kinematics. But yes, there is friction. The friction is what's causing the deceleration, but we don't need to actually calculate that value. So now we're going to do a different version of this problem where acceleration is not constant. Acceleration equals -2 minus t radians per second. So I'll just write that over here. Alpha equals -2 minus t radians per second. So now it's not constant, so we can't use these constant acceleration equations. Instead, we go to our fundamental differentiable relationships, and we'll choose a relationship, and we'll integrate. Okay, so for step 1, we need to find angular velocity. Still, we can follow kind of the same steps as we did before, as far as like find where omega equals 0, solve for t, use t to find theta, but the equations will just be different. So now for step 1, we need to use omega to find t. We will use this equation here and integrate that. So step 1, we will say use omega equals 0, solve for t. So here we'll say alpha equals d omega dt. We separate and get that d omega equals alpha dt. And so then d omega equals, here we'll put the whole thing, -2 minus t dt. And then we'll integrate this from omega initial to omega final. And we'll integrate here from 0 to t final. So if we do this integration now, then we'll get omega final minus omega initial equals the -2 integrated is just -2t. And then the t integrated is -1/2 t squared. And this is evaluated from 0 to t. So if you plug in 0, then there's nothing. And then if you plug in t, then you get what we have right there. So we didn't have to put a plus constant because we knew both bounds of integration. So now we just need to rearrange, and we'll say 0 for omega final equals the -2 t minus 1/2 t squared plus the omega initial value, which is 10. And this is a quadratic equation we can solve for t. So go ahead and solve for t and see what you get. So we solve for this, and this tells us that t equals 2.9 seconds. All right, so here's one of our answers. That is the final time. And now we can use that time and plug into another equation and get theta. So the next equation that we're going to use is omega equals d theta dt, because now we have an expression for omega. And so we'll use that and solve for t. So our omega equation here equals basically all of this. So when omega was 0, we could solve for the t, but in the just omega formula is this. So step 2, we will say use omega equals d theta dt, solve for theta. So here we have omega equals d theta dt, and the omega expression equals -2t minus 1/2 t squared plus 10. So if we move the dt over to this side, and then we integrate, so we'll integrate from 0 to theta and from 0 to t final. And this will be theta final. All right, so we have theta equals integral of all this, so negative t squared, and then we have this 1/2 t squared, which integrates to negative 1/6 t cubed plus 10t, and that should not be an exponent, that is a big t. And that's from 0 to 2tf, so the zeros would just, there wouldn't be nothing there, and we have the t final. So now we're going to go ahead and plug in our t equals 2.9 seconds. So go ahead and do that and see what answer you get. So theta equals 16.53 radians. So we divide by 2 pi and convert that to revolutions. So 16 divided by 2 pi is 2.63 revolutions. So now the wheel has spun 2.63 revolutions. So the last thing we have to do is count. So we'll say count slots. So now what does that correspond to the wheel stopping on if it's gone 2.63? If it goes one full revolution, then it lands on the 7. If it goes another full revolution, it lands on the 7. And so that's now 2 revolutions. And so then if it goes 0.63 more, then an extra 0.1 would be the 8, 0.2, 0.3, 0.4, 0.5, 0.6. So the wheel would have spun to where the 3 is lined up with the needle, and so it stops on 3. So it may seem a little bit tricky there with having to count clockwise if the wheel is spinning counterclockwise, but basically the traveling clockwise when you count is the same as the wheel spinning counterclockwise. It just depends on, if you're following on the wheel or if you're following on the base. So each increment would turn one number closer to the needle.